Hi everyone, my name is Josias. The title of this presentation is Comparing WAG-CO2 injection with continuous water and gas injection in separate wells under uncertainty. Participated of this work Alberto Santos, Denis Schiozer, and Vinicius Botekia. I will start with the background section. Many projects in the Brazilian pre-salt assume the use of water alternating gas injection as standard given the presence of gas with high CO2 content and the lack of infrastructure. WAG injection is an enhancing oil recovery method and an ecologically safety carbon storage strategy that avoids venting and has important features such as better reservoir sweep efficient from the combination of water and gas injection and fluid mobility control. However, the operation of this method in deep and ultra-deep water can be complex and expensive. In addition, previous studies demonstrate the low influence of WAG cycle, and few works compare this method with others for the Brazilian pre-salt. About white and purple section, there are numerous studies in the literature that address the application of WAG injection in scenarios of Brazilian pre-salt. Some reports allow influence of WAG cycle duration as a decision variable in the field development plan, combined with the convergence to long cycles. In this context, continuous injection of water and gas injection in separate wells, called here by CIWG, must else meet such gas recycling demand, promote good recovery and profitability, in addition to present simple operational challenges. However, works that compare such development plans are not common in the literature. The main objective of this work is a comparison of WAG injection with continuous injection of water and gas in separate wells for development and management of a light oil fracture carbureted reservoir subject to pool gas recycling. For this, I consider the UNICIN-2 benchmark model, that is a model that has data of the Brazilian and Gower fields. About the methodology section, we consider this general methodology that was divided into five activities. The activity 1 represents the production strategy optimization for continuous and WAG. The activity 2 represents the G12 cross simulation for G1 of continuous and WAG strategies. And G1 is the design variables, while G12 is the life cycle control rules. So these two activities are part of the optimization process. The activity 3 represents the selection of water's REMs. REM is representative models, right, that represent geological, reservoir, and operational uncertainty. So the activities 4 and 5 are part of the decision analysis. 4 represent the comparison and selection of final production strategies, and 5 performance quantification of final production strategies. So for the activity 1 and 2, I need to consider a hierarchical optimization process because for this work we have a large search space. And another point is that I need to consider some algorithms to assess my best option. In these terms here, I need to consider the ideal AC, MCC, and 2 options to maximize the objective function, that is the net present value, during the nominal optimization of 3 REMs, REM 1, 2, and 3. The REM 1 represents the base case, 2 a pessimistic, and 3 a optimistic scenario. So Here I represent the framework that I consider for the hierarchical optimization process that was divided into 7 phases that represent G1, G12, and your subgroups, right? So based on this framework, I assess my best options, and the nomenclature that I adopted for which RM is CI and WI that represent continuous and WAG applied to G1 and G12 optimization, WCI that represent continuous applied to G12 cross simulation consider G1 optimized for WAG, and CWY that represent WAG applied to G12 cross simulation, considering G1 optimized for continuous. Given that I is always the RDM number, right? And finally, we select the final strategy during the decision analysis based on equation 1 that represents the ANPV, that is the production strategy value, adjusted to the decision maker attitude. So EMV represents the expected monetary value, while this term here and this another one represent the lower and upper scene variance from benchmark B. B is a benchmark return that which decision makers define for your project, and these other two terms represent tolerance value to downside risk and upside potential. Here I have the results of this work. First, I present the NPV risk curve of which strategy, given that B is the benchmark return, and blue represents REM1 strategies, gray represents REM2 strategies, and red represent REM3 strategies, right? So based on this NPV risk curve, you can see that continuous compared to WAG strategies had less flexibility when applied to the REM set, right? This has happened because in general, continuous is on left and WAG on right of this curve, right? Here I am presenting the table 1, the final strategies applied to the REM set. In the previous figure, I present the same results, but in terms of NPV risk curve, right? Now is in terms of NPV, right? Based on this, I have here in blue the REM1, in gray REM2, and red REM3, right? And I highlight here the best options by REM, right? For the REM1, for example, I have C1 and CW1, REM2, W2 and WC2, and REM3, W3 and WC3. So the best strategy by REM in terms of ANPV was always WAC. So this has happened because my best option for this area 1 here is this one, that is CW1. There's another one here, I have W2, and there's another one, W3. That is the best option, right? Here I present the final L placement maps for C1, 2, and 3, and W1, 2, and 3. And with these results, you can see that I have a completely different results in terms of REMs and in terms of developed plans, right? With this case here, just to understand, gray represent producers, blue represent water injectors, red represent gas injectors, and black represent water injectors. Here I present the performance quantification of the best strategies, given that blue represents REM1, gray REM2, red REM3, right? And which is the main idea of this point. So in this previous section, I select the best options by REM, right? Based on this, in this point, I present these best options applying the reference model. This is a real field that we have for this case. Based on this real field, you can quantify the real value of the information, right? For this, the best strategies applying the reference model, WAG in general was the best plan, and two REMs showed closed values. That is these 2 points here, these two cases. One of them divergent, that is this one, which suggests that the plans are closed. Therefore, both can be selected for the case study and possibly for the Brazilian pre-salt oil fields. So this is all. Thank you.